I'm George. I'm from Los Alamos National Lab, and I'll be talking today about running databases with Refinement. Okay, so I'd like to start by lowering expectations a little bit. So the last two talks we've heard have been sort of impressive, fully fleshed out talks with a full paper. This is not that. This is just something I've been playing with in my spare time. I thought it was kind of neat, and I thought I'd try to convince you guys it's kind of neat. So, expectations lowered. Okay, so for those of you who don't like surprises, here's roughly what the talk will look like. We'll start with some background. What are data races? Why do we care? What kind of tools can we use to address them? And then I'll talk a little bit about liquid Haskell, which is what we'll be using for our refinement types. And then we'll go through a few sort of iterations of approaches to solving this problem. And then we'll end with some discussion and quick conclusion. Pretty standard. Okay, so background. So just some sort of personal background. We work at Los Alamos. We have big supercomputers. We want code to run fast and do the right thing. So one of the challenges is when we want code to go fast, we have to do concurrent, mutable shared memory. So we want to have lots of threads accessing the same memory. We have to write code with lots of threads accessing the same memory. And one of the challenges when you're doing that is that you can have data races. So data race is just when you have two concurrent memory operations that are accessing the same data. At least one of them has to be a write, and then it's not some synchronization operation. So this is data that we're using for computation. One of the threads, at least one of the threads is writing it. And the issue is you get non-deterministic behavior that way. Now, not all data races are problematic. There are benign data races where if you commute the operations, you get the same result. And then there are cases where we don't care, but in general, we'd like to have tools to help the programmer avoid them when they are problematic. Okay. So what are some things? All right, yeah, so here's a very simple example. So we'll pretend I'm a physicist, so I suck at coding, and I'm writing a simple one-dimensional stencil, so I sort of hack it up and I think, oh, well, this can run all in parallel, so I make it a parallel for this sort of pseudocode. And of course, there is a data race here, so depending on the ordering of the operations, we'll get sort of drastically different results. And so that's not ideal. So what are some things we could do to prevent this sort of bug from occurring? So one option, the sort of current state of the art is we don't do anything. Like it's up to the programmer, and they're on their own. If they're doing concurrent reads and writes to shared memory, they have to make sure there aren't any data races, or if those data races are there, they're benign. I'm not clever enough to do that, so I would like some help. So one approach is a sort of dynamic approach where we have a runtime that has some sort of explicit notion of regions of memory, say, and then does checks on whether or not those regions of memory overlap at all, and then at a runtime level, we'll decide what things can run parallel and what things have to be sequential. So one of the downsides, this has sort of the standard upsides and downsides of the dynamic approach. One of the downsides is that, especially when you scale up to big machines, this can incur pretty non-trivial overheads. So if you have thousands or hundreds of thousands of cores, even millions of cores, this can really start bogging you down in overheads of reasoning about what pieces of code can run concurrently. It has the upsides, though, of course, that some things we can do statically. The dynamic analysis can figure those out at runtime, and potentially enable concurrency that we wouldn't be able to statically. I'm a big fan of type systems, so let's think about approaches we can use using types to prevent these kinds of bugs statically and avoid some of these runtime overhead issues. So one of the things we could do is we could pull out our favorite dependently typed language and proof system and just prove that our concurrent code doesn't have any data races. And so we build up some abstractions in our language, and then it'll just be up to the programmer to prove for every set of concurrent accesses that they don't have any data races, or that if they do, they're denied. So this is great. It's really powerful. We could do a lot with this, but it's a pretty heavy burden on the programmer, especially if you have a set of programmers who don't even know what this is. That's a big ask. So then there's a sort of middle ground that we could look at where we could use refinement types, and in particular refinement types based on SMT solvers, where we can still get some of the power of the full dependent types. We can specify the behavior of our programs more precisely, but then leave a lot of the burden of the proof up to the SMT solvers. And now we are sort of trying to find the best of both worlds. So we get some static guarantees, but without big proof burdens. So I think, roughly speaking, this is the sort of goal where, for a lot of effort, we can get a lot of safety with dependent types. If we do nothing, we have very little safety, but no sort of upfront effort. Just the sort of horrific debugging of data races at runtime. And then the hope is that this is sort of a good place where we put in a little bit of extra effort for specifying the behavior more precisely, but most of the proof burden is on the SMT solver, but we get a fair amount of safety. So a lot of sort of standard use cases, the hope is that the SMT solver can prove that we don't have data races in some of those cases. Okay, so that's the sort of high-level goal. We're trying to use these refinement types to avoid data races, but without putting a big burden of proof on the programmer. Okay, so our tool of choice for right now is Liquid Haskell. So Liquid Haskell is an extension to Haskell's type system that basically extends it with an SMT logic, which is exactly what we want. So we can refine Haskell types using this expressive SMT logic. Roughly speaking, this allows us to do things like this, where generally if you see these curly brackets, that is a refinement of a Haskell type. So we have some Haskell type, and we have some predicate in the SMT logic that refines that Haskell type. So in this case, if we want to create some new array, then we are specifying that our new array function will take in some list, and then it will return a pointer where the number of elements in the C array corresponding to that pointer will be the length of the list. Then when we go to this is peak element off, is just a fancy mouthful, very verbose way in Haskell to read an element from the C-style pointer, C-style array. So we can now constrain it so that it only accepts indices within the length of that array. One thing to note is that this plen is a sort of phantom measure, so there's no runtime overhead, there's no value corresponding to it. It's just an abstract notion corresponding to the pointer. And it is completely erased type erasure. Okay. Okay, so this is just sort of showing what it looks like when you're actually doing it. So if you do create a new array with hello world, and we try to index into that array out of the bounds of it, we'll get that it's unsafe, and then we fix it, and now we have a D. So that's what we wanted. Okay. So how can we use this to prevent databases? So to start off with, we'll start with the sort of simplest possible thing. So we know a data race occurs when we have two locations that alias, and a data race happens when they alias. So or can happen when they alias. So let's just take. We'll take the property, and we know we can reason about indices into our arrays. So let's just say we can't do any concurrent operations where on pointers where those two pointers are on indices where those two indices are the same. So one thing to notice that is that we'll just be talking about indices. So we won't be doing pointer aliasing directly. I'll talk a little bit more about that at the end of the talk. But just keep that in mind. Okay, so that's very simple in Liquid Haskell. We can just say a index is some natural number, and an alias is some other index if they're the same. So that's easy. Now, so what we're going to do is we have this nice concurrently function in Haskell, which just is from the async library, which takes two I/O operations and returns the pair. So this is the type of the concurrently operation. And we are refining it so that if we take two integers, so we take two indices, and then if they're not the same, then we're okay. So we're just saying, as long as the two indices that we care about are not the same, then we can run them concurrently. So if we pass two indices that are the same, it will not type check. So that's what we do here. So here we're testing it. So we create our new array. We choose a couple of indices into the array. We pass them into our save concurrency operation. And then we're writing those indices here. And so if we happen to pass I and I on accident, then this would not type check, and it would be preventing that data race from occurring. And then at the end, we have a sort of speech impediment version of that little work. Okay. Does that make sense? So we've sort of prevented the kind of data race. Okay, so turns out just reasoning about pairs of pointers is not very useful. So in general, we want to do more than two memory reads, or two memory operations in our programs, I hope. So we need some ability. So for example, if we have a parallel 4, we need some ability to reason about the fact that each of those, so if we have parallel 4 over a set of indices, we need some ability to reason about the fact that each of those indices doesn't alias with any of the other indices. So we need some ability to reason about basically sets of indices. So for that, there's a bunch of things we could do. Just for very sort of preliminary purposes, we're going to just reason about contiguous regions. So regions with a start and an end point corresponding to the set of indices in between. So we can do that here. So we create a region with a start and an end, and we constrain it so that the end is at least as great as the start. That way we can't get sort of backward start and end. And then we define a notion of distinctness, meaning they don't overlap at all. So we can define that in a straightforward way. Overlap is just a sort of standard check to see if two regions overlap. And so now we've successfully sort of encoded that aliasing check into the SMT solver so that it will provide the proofs for us in our programs. Okay. Okay, so now we can write a new version of our safe concurrency function. So now instead of taking two pointers and checking if they're aliasing, we're taking two regions and making sure they don't overlap. So we take one region, we take another region that is distinct from that first region, and then we check if they're, and then if they are distinct, then this will type check and we can safely run them concurrently. So we have a data race-free concurrent function. Okay, so there's a problem here, and I'm guessing some of you have seen it. Here, let's look at the example. Using this first, so we create a couple regions, and then we poke an array into those regions, so we replace 2, 3 with YY and 8, 9 with OO. And if those regions overlap, this won't type check, and that's what we want. So everything's good. Except the issue here, right, so we get our new speech impediment version of Hello World out. And so the issue is that, so R1 and R2, we require that the SMT proves that those don't overlap, but we haven't really constrained the actual effectful concurrency operations to only operate on those regions. So if we accidentally put R2 here, it would still say it's safe, even though it's absolutely not. So we need some way to, there's a sort of disconnect there between our checking that the regions are not overlapping and what the actual effectful operations are doing. And so to address that, we need to refine the effects that our concurrent operations are doing. So right now, we're just defining them as I/O operations, but I/O operations can do anything. And so we need to refine that. And that's sort of like the bread and butter of Haskell programming with effects, is that we want to constrain what effects our programs can have at the type system level. And so now we'd like to do that with these notions of regions as well. So to do that, we use the same sort of trick that we have for pointers, where we have this sort of phantom measure that doesn't correspond to any runtime value. But instead of applying it to pointers, we're going to apply it to I/O operations. So what we're doing is we're refining, we're saying that an I/O up, we're defining a predicate on the I/O operation that is only modifying memory or accessing memory in this region. So then we can define a sort of new safe I/O where we have an I/O operation, but we require that it is only operating, only accessing that region.
Question?
Yeah.
What's the significance of measure? I mean, the term measure?
So measure in general is a liquid Haskell term, and the idea is that it's some sort of, it's often used as a way of lifting Haskell code into the SMT logic. In this case, when you have a measure without an implementation, then it becomes this sort of phantom measure, and then it just becomes this sort of symbolic value in the SMT logic that the SMT logic can reason about, but it's not doing any actual computation. Okay, so now with this, we have our same sort of, we're taking two regions that are distinct as our input, but now we've refined our two concurrent threads with this safe I/O, so that we're constraining this so it only it's only allowed to modify memory in region 1, this is only allowed to modify memory in region 2, and then the result will return a join of those regions, where a join is what you would expect, where we take a new region, which is the sort of min of the start elements and the max of the end elements. And obviously that's an approximation, sorry.
Is that because, you know, a more narrow would be a set of intervals, right?
Yeah, yes. So I'll talk about that at the end. But right now, it's just a sort of first pass. We're just worrying about, we're saying that IO operation can only affect one single contiguous region. So yeah. Right, so now we have what we want, and then of course the semantics is the same. We just refine the type. And now, if we run it, so now if we accidentally, so here we create a couple of indices, and then we create singleton regions for those indices, and then we are writing into those regions. So now, remember before we had the problem that if we accidentally got these wrong, the type system wouldn't catch it because it wasn't sort of combining, it wasn't relating the regions that we're comparing for distinctness in the type system with what the IO actions were actually affecting. And now they are. So we have this poke this poke is also using the safe IO construct where it is only affecting the singleton region at I. And so this will all type check, and then if we accidentally had two I's here, it would not type check, and we'd effectively have detected the database. And then I also add just this sort of sequential version where here we have the same sort of safe IO construct, but we don't have the requirement that the regions are distinct. So we can define sequential operators as well, where the return type of this will be the same sort of join. So we're sequencing two region IO operations, and but we don't have the requirement that they're distinct because we've defined a sequential semantics, so there's no database. Okay. So that's the sort of, I think if there's one kind of cool thing from this talk, is this idea of using this ability to refine Haskell types on actual Haskell effectful types like the IO monad. So we're refining the effects, but in this SMT logic, where as opposed to doing something like a state monad where we're just encapsulating the state directly. Okay. Okay, so we're going to end a little short. So I'd like to discuss a little bit the sort of drawbacks and what I think is interesting sort of future work in this area. So the first thing is that remember that a data race is only a data race if at least one of the operations is a write operation. What I've shown so far is just doesn't have any notion of permission. So it's basically right now, if you have concurrent reads to overlapping regions, it will claim that as a data race when it is not. So you definitely want to incorporate some permissions. So for example, one of the solutions to the stencil computation example early in the talk is to do a sort of double buffer, but even that would be prevented by this approach because we have overlapping reads and we claim it as a data race when it's not. So you definitely want to have some notion of permissions. And this isn't too hard to add, pretty straightforward. Then of course, the restriction to only have an IO operation be accessing a single contiguous chunk of memory is really unrealistic and not very flexible for real-world programs. So you definitely want some notion of multiple regions, reading and writing from multiple regions to extend this. And so there are some notions you might want to have this sort of set of contiguous regions potentially. The SMT solvers do have some ability to reason about set operations, so I think this is definitely possible. Just haven't gotten there yet. So another interesting, I think really important feature that is sort of lacking in Liquid Haskell is the ability to incorporate the witnesses from the SMT solver. So SMT solvers, I didn't really describe what they are, but you can think of them as sort of, they find values that satisfy some constraints. So generally, if you're declaring some property like x is always less than x than 1, it will search for x is always less than x plus 1. It will search for a counterexample, and then if it can't find one, that will provide the proof that it is. And then if it can, then that counterexample should inform the developer of, hey, there is so in the example of the data race, you might want to see, hey, there is a potential data race. Here's the example of where it could happen. Right now, though, that tooling doesn't seem to be there quite yet. Sparse regions also, so we've only been talking about contiguous regions, but of course, you're definitely going to run into cases where those don't describe the data you want to do operations on well at all. So yeah, I think that's my guess is that there's some ability to do that, represent that in the SMT solver, but I definitely haven't figured that out completely yet. Another interesting area, so Liquid Haskell is a sort of pre-check that is totally independent of GHC. So all of the Liquid Haskell checks are comments, so GHC doesn't see them at all. It doesn't affect the code in any way. But I think one interesting area is, right now we've been having the programmer say, this is something that should run concurrently, check that it's safe to. But you can imagine incorporating the result of the SMT solver into a choice about the code gen. So you can imagine checking if there are potential data races. If there are, define a sequential semantics that is applied. And then if there are no data races, provably no data races, then run them concurrently. And then you start to get a sort of concurrent program that is provably equivalent to a sequential semantics. And then we've been talking about applying this to low-level, Haskell code modifying C arrays. But you can imagine applying this to embedded languages as well. So I think both domain-specific and general-purpose languages. So for example, there's the Ivory language out of Galois, where they embed basically a C-like language in Haskell, and you can imagine applying this sort of technique directly to that, and then you would get sort of really low-level code that is both memory safe and data race free, and I think that's a sort of exciting area. And then finally, we have, one more thing that we haven't addressed is the notion of, so we've been just reasoning about sort of aliasing at the index level, but you can also imagine aliasing within a data type. So if you have a struct, you want to be able to access different parts of that struct concurrently. Right now, we have no sort of ability to do that. I think that should be possible, but it might be a little hairy. And then also, the sort of core idea is using the SMT solver to reduce the burden of proof on preventing data races. And another tool I think would be useful to look at is, instead of refining the Haskell type system to be more expressive, we can take a sort of subset of a full dependently typed language and use an SMT solver to prove certain data race conditions hold for that logic. So the SMT calc, I think, would be an interesting sort of different path you could take in the same vein. Also, one thing, going back to the multiple regions, so we've been talking about index spaces, but I haven't really talked about, I've been sort of assuming a global array, a single global array, and just reasoning about indexes within that. But if you have multiple allocations, sort of multiple C arrays, you also want to be able to reason about those. So say if you want to read the first 10 elements out of one array and then write the first 10 of another array, you need some ability to reason about the sort of the different allocations and some way of encoding the invariant that the mallocs for those different allocations are all distinct. I think that's a pretty hard problem in this setting, at least in the sort of liquid Haskell setting. That global invariant is a tricky thing to try to encode. I think it may be easier if you start moving into the embedded language setting, where you can potentially encode that sort of invariant. Okay, so in conclusion, this is a small step towards, basically this is, I think, hopefully you're convinced that this is at least a sort of possible thing to do. I think it's a small step towards getting more correct shared memory concurrency, where we're preventing data races where we can, doing it statically, and sort of using this ability for the SMT solver to reason about the effects that our programs are having and prove that they don't have data races. Okay, that's it. Questions?
So, if I understand correctly, you're effectively using these sort of like intervals as some kind of way to model regions of memory, right? What if you were getting, say, parallel computation from trees or other pointer data structures where you didn't have a nice set of indices that you could use as a way to describe things?
I think there's a wide. The majority of cases you won't have those nice intervals, I agree. I think capturing in an SMT logic sort of every possible case, I think would be hard. I think you probably have to come up with a specific, right, so depending on the data type, you probably want a specific way of encoding the memory, the regions of memory that can be accessed for that. And I think for inductive data types like trees, trying to do that with an SMT logic will be hard.
And I think there was a lot of work done on this problem 20 years. There were like these pointer, these path-based approaches, right? And of course, then there's the effects, right? And that's where effects came from.
Yeah.
The original papers were about figuring out that two sub-computations and then divided non-parallel could actually be non-interfering parallelized. Yeah. And effectively, like unintended, they were trying to distinguish between regions of memory, right? Which is really what you're doing is you're doing it on a different thing.
Yeah.
So I agree that refinement types are something like a really nice way to bring some advantage of dependent typing to a broad audience. You also seem a bit reluctant to say that you expect physicists to use Haskell, liquid Haskell. So do you have thought about how to make this more accessible to your average physicist?
That's a really good question. Not really. I think.
Liquid forecast.
Yeah, I think one of the things I'm hoping to do. So one of the interesting applications I think would be to apply this sort of technique to maybe not in the refinement type setting, but using SMT solvers to reason about data races at something like the LLVM level. So LLVM has some ability to integrate with Z3, so potentially maybe you could completely sort of put zero burden on the physicists can still write as Fortran, and then via the compiler pass, you could potentially sort of apply some Z3 reasoning to the LLVM IR, and hopefully, I think that's limited. I think being able to build up the abstractions to sort of guide the SMT solver, it will be more powerful. But yeah, maybe applying an SMT solver to an IR as a backend for Fortran, whatever the physicists can write, may be more fruitful. Yeah.
In a sense, wouldn't that also be a good place to, as mentioned, either domain-specific languages or, I guess, embedded EDS also be a little bit difficult for Fortran, but you know, sort of domain-specific language that they could use possibly externally, but would be, you know, say the pattern of access or specified somewhere else or something like that.
Yeah.
Just make it like you have these 5 things, not like you have to learn Haskell.
Yeah, definitely. Yeah. I think that's a good point too. I think my experience is that pushing domain-specific languages, at least at an institution like ours, can be painful. But yeah, I think that is a compelling path forward. Is if you can define some domain-specific language for which you can reason effectively about the memory access patterns, then you can potentially say much stronger things about, prove stronger invariance about databases.
You mentioned exploiting the invariance that improved in SMT solver. Actually, in the old days, actually SML was translated exactly by first type checking and then throwing all the information out that way and implementing as if it were a scheme program or a list program. Until people like John here come out and realize that, well, you know, we can exploit, you know, the memory invariance that was shown for getting untapped data structures, various kinds of things. For region-based memory management completely surprising. So I was just wondering, you were indicating actually it would be good to have actually the invariance that you used in generating code. Can you give some examples where this in this domain would be interesting to say, you know, here, apart from array panels checks, how can you exploit some of the SMT verified invariance in compilation?
Yeah, so I think that's a good question. So one area that I've thought about a little bit is in sort of automatic memory management. So if you can reason about memory access patterns directly, in addition to preventing data races, you could also potentially, one of the hairy things in programming our machines is moving data sort of between GPUs and different HBM nodes and PDR memory. A lot of that has to be done manually, and so making that potentially a little more automatic by using the sort of knowledge you've gained about memory access patterns via the SMT, via the refinement types or SMT logic or whatever, then you can potentially reduce that burden or automate some of that sort of painful manual memory management. That's one. Well, there's probably others. I haven't thought super hard about it.
Yeah.
So have you thought about how what you're doing here might compare to like designing a language with an abstraction where you just don't write programs like that, where you wouldn't have that sort of data race?
Yeah. So I think no, I haven't thought about it a lot. So we work in a setting where everything is written in Fortran or C. So we take as an assumption that you're going to write mutable shared memory imperative programs, concurrent mutable programs. So my gut instinct is that there are cases where for performance reasons you will have to do that. As far as sort of constraining your domain, constraining the kinds of programs that you write in a way that you can get performance for that class of program. Like if you write a domain-specific language, you can potentially always generate high-performance code. I think that's one approach, but for sort of general-purpose programming, my instinct and my understanding of the sort of state of the art of the literature is that there are cases where you have to drop down to write parallel mutable code to get good performance. But that may be changing, as we just saw.
Anyone else? Great, thanks, Rich.